And you began this in graduate school, if I remember correctly.
Yes.
And that whole group. With who's the head guy on that group?
Brian Schmidt. And Bob Kirshner.
Bob Kirshner, right.
And the Chilean group for the Kalantololo, which you know very well.
Right. Mm-hmm.
And so what changed the game was in the 1990s, we both came to realize this class was special. It wasn't like the other supernovae. And the advent of large cameras by those standards on telescopes that had a big enough field of view that you could simultaneously stare at 100,000 galaxies and actually have a chance to do this experiment, actually find supernovae on demand.
Right. So you didn't have to wait around for one to show up and then look at it.
Right.
You would we're going to find 3 supernova tonight.
Right. And it was actually quite amazing because back in the day when the Hubble Space Telescope was a new thing and it was incredibly valuable to get time, we would propose for time and say, we'll tell you exactly where the supernova is on Tuesday, so you could start observing it Thursday. And they were like, "You're gonna what? Like you're gonna tell us where a supernova is on Tuesday?" And we're like, "Maybe Monday night if the computer's operating fast enough."
And they're like, I got a dinner. Can we hold that off?
But it was, if we had bad weather or something, it was scary too because it was like, and if we don't just stare at blank sky, which is no astronomer wants to use the most capable facility to just stare at nothing.
Right.
This type 1a supernovae are visible halfway across the universe.
That's right.
But they're only useful as a standard candle once you can calibrate those that are closer, that have some overlap maybe with the Cepheids. Is that right?
For the discovery of the 1990s that the expansion of the universe, and here's the big spoiler alert, that it was accelerating, not decelerating, you don't even have to calibrate them because you're only using them as relative measures. You're saying how much was the universe expanding back then relative to how much it's expanding now, even if I don't know an
that
absolute
basically
number.
divides out.
It divides out.
There.
It's like Neil is handsome, but relative to me, not so much.
Okay.
I'd forgotten that's important.
It's a very important. So the two stories we're going to tell disconnect in that way.
Yeah.
And so by the late 1990s, even if I didn't know the true luminosity, was it 10 billion solar luminosities or 8 billion solar luminosities? What I could say is, that distant one was so faint that it is, 10 times further away than this one, whatever the true
But you've got
luminosity
you've got a
was.
history or an experience of sort of
so you got a whole string of pearls through time and space.
It's almost like you're a super
clean.
sleuth in a way.
Yes.
It's like you're a detective sort of using evidence.
Yes.
But within the distance ladder, you have these 3 rungs, and what strikes me is 4 rungs. Sorry, you have.
But this is, to be clear, this entire discovery of the accelerating universe only depended on one rung internally to itself. So
but if a Cepheid is, I've sort of got a, so if dust affects its brightness, right?
That's important.
So now that rung is sort of there's some weakness in that rung which can propagate through the rest of the distance ladder. So how are we accounting for? There's so much we don't know, dust, right? Or other components that could sort of affect one rung of the ladder could then sort of throw off the entire calculation.
Or even dust even in your relative comparisons, the dust would give you the wrong distance.
Right. So when I was a graduate student, this was the part of my thesis was to figure out how to contend with dust in these type 1 supernova observations. So it turns out that dust makes things dimmer, which would fool you into thinking it's further away. That's very bad. Okay, but it does something else too. It makes light look redder when the light passes through it. So look at a sunset, right? Not only does the sun look dimmer, but it also looks redder.
So if you're seeing the red, then you know there must be dust.
Exactly.
But then how do you determine how much dust?
You look at some supernovae where there is no dust, like it's way far out of its galaxy, or it's the bluest one you've ever seen, or something like that.
So the power of the red
against the dust metal.
The redder it is, the more dust.
Right.
Yeah.
And in fact, if you really do this right differentially, all you need to know is it's so much redder than other ones, and then that affects how much difference it is in
it's
distance.
like that you're sort of you're getting these pieces of evidence and building. That's fascinating to me.
So much science happens that way. People think it's just one question and one answer and one experiment.
Yeah, it's techniques.
Oh my gosh.
So much.
Well, what's striking me in all of what you do, not so much Neil, but you, is you hit a roadblock and find a way around it.
Right. Yeah, it's all solving problems.
We need clever people.
Yeah, exactly.
On the team.
It's fascinating.
Okay, so now, if I remember correctly, the goal wasn't so much to measure this Einstein
No.
term, was it?
No idea. No, in fact, it wasn't even on my radar screen.
It was just to lay it out. It's just to see what's going on.
It was just to measure how much the expansion was slowing.
Okay.
Right? And was it slowing
So tell me about
enough
your equations.
Yeah.
Tell me what you wrote stuff.
I wrote stuff down. Yes.
Okay.
So I wrote down some standard equations of what should have worked for the data, which is
equations anyone would know. Just I want you to know.
And you thought you were thinking it was slowing down the expansion.
And not only that,
going
I was
into
so
this.
sure it was slowing down because that's what everybody told me, and I was in graduate school at the time, was that I said, okay, so the supernovae will measure the slowing, and I'll immediately convert that to what is the mass density of our universe, this famous number called omega m.
And then apply that to our universe and extrapolate.
Right away, yes, but right away that number tells you what we want to know. If omega m is greater than 1, there's so much matter in the universe, it will recollapse. If it's less than 1, it will expand forever. Omega m equal 1 is called a critical universe, or the critical, it's the mass it's the gravity mass that the Earth would have to have to launch a rocket and have it be escape velocity.
So is this the big freeze, the big rip, and the big crunch?
No, we'll get to that.
Okay.
We'll get to that.
Right. So can you catch up? Because I'm
working on it.
So anyway, too slow for you.
Jesus,
So I had a
come on, guys. I got stuff to do. There's a supernova happening in an hour.
Yeah, that's a good point. You've been listening. So there's a very simple sequence here. Is supernova measure deceleration related to how much matter is in the universe that's causing the slowing expansion.
Mm-hmm.
So when I wrote my computer program, I said, hey, computer, fit that and tell me the answer. And the answer it spit back was negative mass. Okay.
Whoa.
Now there's no such thing as negative mass. That's not like a physics option. But computers don't know physics. And so you give them very simple instructions, measure deceleration, turn into mass. And I hadn't yet noticed that the data was saying the universe was accelerating. So it was like, okay, you want me to make that equation work? I'll just flip the sign over here on matter. Now it's negative. And I'm like, that isn't right. You can't do that in physics. We can't report that. And so after doing a lot of checks, I was like, well, what could do that? And then, it was like all the classes we ever took was like, Einstein once had suggested something that could go the other way. You put that into the equations and it fit like a glove.
Bada bing.
Yeah.
And you've got, it's not just expanding, but it's accelerating in its expansion.
Correct.
And now it's Y, and that gets you to dark energy.
Right. And so what is it? So,
you made the measurement that it exists.
Right.
Which is a separate thing
absolutely
from knowing what it is
from the
measured.
Interpretation. Yeah. And,
right.
And just to mention,
people need to needs to sink in here because
the universe is accelerating. Whatever's doing it,
we can make measurements of things even if we don't know what's causing it.
Well, it's how some of the greatest things happen. So you're going for A, and then you find B, and this is going to sound as a writer in a room in comedy shows. You could give us an assignment, write a joke about, I don't know, airplanes travel, right? And nothing great comes. And then just out of that comes a great side bit that ends up being, that's how the Back in Black segment came about at the Daily Show. Because
Louis Black.
Yeah, because we were trying to come up with great jokes on these little stories like a Florida man. And we're like, we don't know what to do with this. We're like, give it to him and let him rant. So it's the same, it's obviously in the arts, but it's the same thing. You're going for one thing, and in a beautiful way, it's like a beautiful mistake in a way, or whatever.
But it's also the thing that still to this day we don't know for sure or understand well. I mean, we could say the universe is accelerating. There's no question about that. But what is causing it? We're still relying on Einstein's cosmological constant, or more generally, dark energy. But we don't understand the physics of that at all.
Well, get back to work, dude.
Yeah. Well, I'm an
what are you
observer,
doing
so-
here?
You made the discovery. Now I expect part 2 of this.
Oh yeah. Well, actually, there's something stuck in my pocket.
What?
I've been sitting on it, and it's bothering me. You ever get like a pebble?
Yeah.
What?
And you're sitting, and it's like, oh yeah,
Whoa!
this.
Wow.
Wait a minute.
There you go.
Wait a minute.
Wow. Did you buy that on the street?
Wait. Yeah,
Actually, it's in the gift shop downstairs.
I got a guy.
Don't bite it because it's
who's got
chocolate.
bling that's bigger than this. At the club.
So
hanging out with
just
with the
for
children.
context,
wait.
right? They didn't give us the Nobel Prize for discovering dark energy, but for discovering that the expansion is accelerating. Yeah.
Right.
Right.
That's why if it would be bigger if it was
It would
more
be like
significant.
double the size.
It's just a little discovery, so they give you the baby. This is the baby Nobel Prize.
That's right.
I'm sorry.
That's
So this, I guess that's Alfred Nobel on
Yes,
the cover.
it is.
Right.
On the
Yeah.
cover there.
Yes.
Very cool.
Yeah.
Is this actually gold?
Yeah.
Or is it gold like
Let me
Well,
touch
it's
it.
it's I don't know what it's 18 karat or something.
18 karat?
I know it's worth
He
a
gave
lot
it to me.
today.
He gave it to me.
It's worth a lot today. Have you seen the price of gold?
Yeah, 4,000.
I'm worried walking out on the street with this. There's a funny story about
Like the
Brian
game
Schmidt
show.
taking his on the airplane, and the TSA agents were very confused because when they X-rayed his backpack, it just showed up as a hole in his backpack because the gold
doesn't
just
go through.
absorbed all
right.
the X-rays,
Yeah,
and they're
it
like,
doesn't go through
"What
it
is
at
in
all."
your backpack?" And he was like, he took it out, and they go, "What is that?" And they said. He said, it's a Nobel Prize. They said, who gave that to you? He said, the King of Sweden. What did he give it to you for? For discovering the accelerating expansion of the universe. They were deadpan. Though. So
Basically, this guy discovered that you wouldn't be here if I wouldn't be talking to you right now. Can I just say something? You're brilliant, and I'm impressed with that. But I'm more impressed that you're walking around New York City with that in your pocket.
I hear people are nice here.
So then it doesn't come with a thing around your neck
No.
like the swimmer, you know.
Yes, like
yes.
it's Mark Spitz. We had 7 of them. or whatever.
Stay modern here.
No, I'm going with Mark Spitz.
Michael Phelps.
I was a
Michael
swimmer.
Phelps.
Michael Phelps.
Michael Phelps.
Yeah.
This is heavy.
Yeah, so it's probably
This
got at
is
least a little.
this is
we got to give it to Archimedes
Nobel.
and figure out how much gold is actually in it.
And Neil, where did the gold come from that was in it?
Oh,
wait.
supernovae! Oh my God!
It's all
Come
coming
on.
full circle.
Oh, full circle.
Wow.
They said, in fact, they said, we want to give you something that really represents the work you did. And they was like, let's find a supernova by Tuesday and we'll get some
There you go.
little bits and we'll make something.
Oh.
Listen, I know a guy that can melt that down into a watch if you want. That's beautiful.
You surely know here at the American Museum of Natural History in our backyard, it's our yard, but it's run by the city. The city controls it, including the dog run. But there's a monument there put there by one of the Swedish
Right.
pharmaceutical companies.
In the Teddy Roosevelt park.
In the park, and
Yes.
it's in honor of all the American
Yes.
Nobel Prize winners. And my boy's name is on that statue.
They're all carved.
They're
there.
chiseled in.
Yeah.
My boy's on that statue. Right there near the dog
I
run.
lived right.
Are you saying dogs watch it as they poop?
Did it pee?
So what? We live on 79th Street, right around the corner from here.
yeah.
My dog pees on your name all the
Really?
time. I'm sorry.
No,
I didn't
my
mean
name
to-
is actually pretty high up. You would have to.
I have a very big
seriously
dog.
climb up.
My dog is well endowed. That's all I'm saying. He can reach high.
Okay, so say what you said again because it's important. You got this
Right.
not for knowing what dark energy is,
Right.
but for the discovery that it exists.
For the discovery that this phenomenon, the universe accelerating, exists, which everybody attributes to dark energy because normal gravity from matter doesn't do that.
Doesn't do that.
It goes the other direction. It's
It
like
goes the other
having,
direction. Hence
it's like
your
driving
negative sign that showed
right,
up in
it's
your...
like having a car and like all you've ever done is hit the brake and then one day the car just takes off and you're like, how did the brake do that? And it's
Yeah,
like, no, a
yeah.
different pedal, the gas pedal did that.
And I think you've started to move toward the idea that dark energy determines the fate of our universe, right?
It
And
does.
that's where it becomes, which makes you a real Debbie Downer. But there's big freeze, there's
Yes.
big rip, and there's big crunch.
Yeah.
Which actually feels like Ben and Jerry's anxiety flavors. Like,
Yeah.
you would be the big freeze because you're closed off emotionally. You would be the big rip. You're strong, and I'd be the big crunch because I'm a baby. And everything collapses.
The big crunch, I think, is not in the cards.
Actually, everything's on the table still, to be honest with
Really?
you. And in light of some more recent results on dark energy where it may look like it's thawing or weakening.
Well, let's get into that.
So we will.
Let's
We
get
can.
into that
Yeah.
right now. We're all up to speed now.
Yes.
And we have like 3 minutes left.